Hello everyone, this is the output video of my internship project on battery health solar power systems. After completing the database design, battery health analysis, machine learning prediction, charging optimization, and peak load optimization, I integrated all of these outputs into an interactive Power BI dashboard. The dashboard consists of 4 pages that help monitor battery performance, predict battery life, and support energy management decisions. Here is page 1, the executive summary. The first page is the executive summary dashboard. It provides high-level overview of the overall battery system and its performance. Here first you can see there are multiple KPI cards. The first KPI card is the total batteries. This KPI displays the total number of batteries currently being monitored by the system. Next is average SOH. This card shows the average state of health of all batteries. In my project, the average SOH is approximately 82.85%, indicating most batteries are still in operating and good condition. Next is followed by estimated cost savings. PI represents the estimated reduction in electricity cost achieved through charging optimization and peak load management, followed by peak shaming amount to KPI card. This card shows the total electrical load shifted away from the expensive peak hours, reducing demand on electricity grid. For last but not the least is the max capacity fade, which indicates the highest battery capacity loss observed during the analysis, helping identify batteries that may require maintenance. As we come to the main graphs, this chart compares the average state of health of each battery, making it easier to identify high performing and low performing batteries. Second one is SOH degradation across charge cycles. This visualization shows how battery health gradually decreases as number of charging cycles increase. Next is capacity degradation across charge cycles. This graph illustrates the reduction in battery capacity over time due to repeated charging and discharging. Last but not the least is capacity fade comparison. This chart compares capacity fade across all batteries, allowing us to identify battery experiencing faster degradation. Here, the filters are interactive filters that allow users to analyze specific batteries and customize the dashboard based on different conditions. On to page 2, which is battery operation dashboard. The second page provides the real-time view of battery operation condition. It helps operators monitor changing status, battery temperature, voltage, and state of charge, enabling timely operational decisions. First KPI card is maximum SOC, which displays the maximum state of charge record among all batteries. Verify that the batteries are reaching their expected charging capacity. Next is average temperature. This card shows the average operating temperature of the batteries. Monitoring temperature is important because of excessive heat and acceleration degrades the battery life. Moving on to average SOC, which represents the average state of charge across all batteries. It gives the overall indication of the available stored energy in the system. Last but not the least is average voltage. This card displays the average battery voltage, which helps verify batteries are operating within their normal voltage range. Next, charge gauge. The gauge provides a quick visual indication of the current average state of charge. In this project, the average SOC is approximately 70%, which indicates that the batteries have sufficient energy available for operation. Next is average current by battery. This chart compares the average charging or discharging current of each battery, allowing operators to identify differences in battery usage. Next is average associated by battery. This visualization compares the average state of charge for individual batteries, making it easier to identify the batteries that require charging. Next is voltage measure over time. This graph shows how battery voltage changes over time. Stable voltage trends indicate healthy battery operation, while sudden drops could indicate battery faults. Moving on to temperature measure over time, which monitors the battery temperature continuously. It helps detect overheating conditions before they affect the battery's performance. Next is battery recommendation distribution. The recommendation distribution summarizes the charging recommendations generated by the optimization model, such as charging using solar energy, normal operation, charging immediately, or by using stored battery energy. The filters users can filter the dashboard by battery ID, recommendation type, and state of charge range to analyze the individual battery performance. Moving on to page 3 is battery failure prediction and remaining useful life dashboard. This is the forecast dashboard. This focuses on predictive maintenance using machine learning. The dashboard displays remaining useful life prediction and battery failure analysis generated by random forest and prediction model. The first KPI card is average SOC, which displays the average battery state of charge across the selected batteries. Next is healthy batteries. This card indicates the number of batteries currently classified as healthy based on their operating conditions and prediction results. Next is remaining useful life. This KPI card represents the remaining useful life generated by the machine learning model. The least is the average of remaining useful life days. This card displays the average remaining useful life of all the batteries in days. This is the plot on battery health versus the remaining useful life. Specialization compares battery health with the predicted remaining useful life. Batteries with better health generally have a longer remaining optional life. Next is the bar chart, which represents the remaining useful life by the battery. This chart compares the predicted remaining useful life for each battery. It helps identify batteries that may require replacement earlier than others. Moving on to the battery status distribution. This chart classifies batteries into excellent, moderate, and needs attention categories, providing a quick overview of the overall battery health. Next is our remaining useful life degradation over charge cycles. This graph illustrates how remaining useful life gradually decreases as charging cycle increases. This trends help predict when battery maintenance or replacement will be required. Not the least are the failure risk distribution. This visualization separates battery into healthy and high risk categories, allowing maintenance team to prioritize batteries that require immediate action. Here, the filters user can use these filters by dashboard for battery ID, battery health status, failure risk, and charge cycles for detailed analysis. The last dashboard is the optimization dashboard called as the Smart Energy Optimization Dashboard. The fourth focuses on mainly energy optimization. It combines the result of charging optimization and peak load optimization to improve energy efficiency and reduce electricity costs. The KPI cards are first peak shaving amount. This KPI displays the total electrical load shift away from the expensive peak demand periods. The peak shaving help reduces the demand charges and improve overall energy efficiency. Next is dependency. This chart shows the percentage of energy drawn from the electrical grid. This project, the grid dependency is approximately 33%, indicating that most of the energy demand is supported by renewable solar energy and battery storage. This is solar usage. SPI represents the percentage of energy supplied directly from the solar generations. A higher value indicates a better utilization of renewable energy. Next is cost savings. This card estimates the reduction in electricity cost achieved through intelligent charging and battery dispatch strategies. Next is average electricity tariff by peak period. Charge compares the electricity tariffs during peak and off-peak periods, helping determine the most economical charging schedules. Next is battery usage across time slots. This visualization shows how battery usage changes during different time periods, such as daytime, currently operating time, and night off peak. Next is battery dispatch distribution. This chart summarizes whether the system recommends using battery power or drawing electricity from the grid. Next is the bar chart. This chart displays the frequency of different charging recommendations, like charging using solar, charging immediately, normal battery operation, and use batteries. Next is the visualization. This visualization recommends the shifting flexible electricity loads such as EV charging or water pumps or off-peak hours to reduce electricity costs. Last but not the least is the donut chart, which summarizes the overall distribution of optimization recommendations generated by decision support systems. The filters include for battery ID, time slots, recommendation types, and battery dispatch mode, allowing users to analyze the optimization strategies under different conditions. Overall, the Power BI dashboard integrates the output from all the previous lab into a single interactive platform. And this makes informed decision and make for helps in efficient solar battery management. Thank you.